Hey everyone, welcome to the First Force seminar. Thank you for joining us today. I'm Kara Brugman, a research scientist and outreach coordinator for FORCE. And this seminar series was organized by myself and research scientist Kyusei Tsuno, who couldn't be here today because he's actually in Japan, where one of our multi-anvils is having final testing. Before Dr. Tracy begins, I just wanted to remind you that this meeting is being recorded and it's going to be available on YouTube next week. So if you know of anyone who missed it, you can direct them there to see. You could also follow us on Twitter, LinkedIn, and Instagram to get updates, or you can join our mailing list at our website, force.asu.edu, to get updates on all of our events. And speaking of which, our future seminars, which are held Fridays at noon, our next one will be given by Bin Chen from Hawaii on Friday, April 28th, followed by Yingwei Fei on Friday, May 19th. Okay. So Dr. Sally June Tracy is a staff scientist at Carnegie's Earth and Planets Laboratory. Dr. Tracy received her PhD in material science from Caltech, and she joined Carnegie after a postdoctoral fellowship at Princeton. Dr. Tracy's research spans mineral physics and material science using both static and dynamic compression techniques coupled with X-rays. So Dr. Tracy, you can take it away.
Okay, well, thank you, Kara, so much for the introduction, and thank you so much for inviting me to share some of my work this afternoon. My plan is to hopefully give you a flavor for some of the recent experiments I've done using dynamic compression to look at high pressure temperature crystal structures and melting behavior of different minerals. And then at the end, I'll talk briefly about some of the ways in which I think that high pressure synthesis can be a real benefit to this type of experiment, and mention some examples of ongoing projects that use various high pressure synthesis techniques. There we go. As it turns out, the fast timescales and extreme pressure temperature states that we can get to using various dynamic loading methods make it a really good tool to study a wide range of processes in Earth and planetary science. And so this includes things like the synthesis of high pressure phases that are only found in the deep interiors of planets. But dynamic experiments also allow us to investigate things like impact phenomena. So for example, investigating things like shock metamorphism, or looking at samples from impact craters or meteorites, for example, and trying to understand the structures that one might observe. Briefly, to take a step back, for those of you who may not know a lot about dynamic compression experiments, a shock wave, which is one of the main techniques that we use, is simply a supersonic wave that produces a step-like increase in pressure, density, and particle velocity as it travels through a material. Can you see the pointer? Maybe not. I'm trying to make it the laser pointer.
Okay.
There we go.
Yep.
And so this cartoon here sort of depicts sort of a train accident that could be thought of as analogous to a shock wave moving through a material. So here, after the initial impact event, the shock wave travels through the series of train cars at a velocity that is faster than the velocity of any of the train cars moving behind it. And so the shock front travels at the shock velocity US, and the material behind the shock front travels at what we call the particle velocity, or UP. And so this sort of gives rise to sort of a pileup of cars behind the shock front, which would be analogous to the high pressure state in our material. And then eventually, at later times, we're always going to see a release wave catch up with the shock front. And so the shock state is transient, having sort of a finite lifetime. And so if we proceed to sort of apply conservation laws across the shock front, this gives us this set of equations known as the Rankine-Hugoniot equations shown here. And so this is just a result of applying conservation of mass, energy, and momentum across that interface. And these are really important to shock physics because they relate these velocities, the shock velocity and the particle velocity that we can measure in an experiment to physical variables that we might be interested in, for example, pressure, density, or energy. When we shock a material, we put ourselves on a curve known as Hugonio. So basically, we're instantaneously bringing the material to a high pressure temperature state on this sort of red curve shown here. And what you can see from this is that compared to a constant temperature isotherm shown in blue, the Hugonio actually defines both a steeper curve in pressure volume space, but also involves significant heating. And this is simply because in these rapid experiments, there's no real time for heat flow out of the system. And then furthermore, on release from the Hugonio, we actually follow what's sort of a quasi-isentropic pathway shown here in orange. And so while the pressure quenches rapidly, the temperature can remain high for some time. And so this actually has important implications for understanding and interpreting sort of post-shock modifications that we might see both in natural samples as well as shock recovery experiments. So how do we go about generating shock waves in the laboratory? One technique to do this is using an instrument known as a light gas gun. And so using this type of instrument, we can accelerate projectiles to high velocities up to around 8 kilometers per second. And those impact our sample, and that generates a shock wave in the material of interest. And so how this works is that we have an explosive charge that detonates, and that drives a piston into a pump tube, which is filled with a light gas, usually helium or hydrogen. And that light gas is compressed to some threshold pressure, at which point a burst disk that separates the gas-filled pump tube from an evacuated launch tube breaks, and that has the gas expand into the launch tube, sending a projectile that accelerates down that launch tube and impacts our target at the end of in the target chamber. And so with this type of method, we can accelerate projectiles to high velocities and generate shock pressures up to a couple hundred GPa. And these typically have experiment durations on the order of hundreds of nanoseconds up to sort of the microsecond regime. And typical sample sizes are millimeter thick samples with centimeter lateral dimensions. A second technique to generate shock waves in the lab involves using high-powered lasers. And here we're using a focused laser to generate a ablation-driven compression wave in the sample. So basically, we focus our laser onto what is usually a low Z ablation layer, which is affixed to the back of our sample. And that generates a plasma in that layer, and that plasma expands backwards, and that sends a shockwave forwards into our sample. And so using this technique, you can actually get to incredibly high pressures up to the terapascal regime. The caveat, though, is these experiments tend to have very short durations, typically only a few nanoseconds. And so oftentimes we're interested in a process that may not occur, for example, on that type of short time scale. And with these experiments, we're using smaller samples, typically on the order of tens of microns thick with millimeter lateral dimensions. So for these types of very fast loading experiments, the traditional method to collect information on this sort of nanosecond to microsecond timescale is using velocimetry techniques. And so with this type of technique, effectively what you're doing is you're reflecting a laser off the moving sample surface. And then using the Doppler effect, you can then derive information about that surface velocity as a function of time. And then with that, you can determine both the shock velocity and the particle velocity. And then using those conservation equations I mentioned previously, that allows us to determine the continuum pressure density state. And then doing a series of experiments, we can then sort of map out that pressure volume Hugonio curve, which gives us information on how the continuum properties of the material change with increasing compression. And so using this type of method, as I mentioned, you sort of get a continuum picture of what's going on, and then you can sort of oftentimes identify what are sort of kinks in that pressure volume Hugoniot curve, and oftentimes attribute those to phase transitions. However, we don't have any crystal structure information from this, and oftentimes when you have phase transitions that may have small volume changes, it's difficult to see that with these types of measurements. Alternatively, you can also look to doing shock recovery experiments and collect samples that have been shocked and analyze them using different techniques, be like microscopy or diffraction. However, as I mentioned, because we go through what is sort of a high temperature release process, it's actually fairly common to see post-shock structural modifications, which can even include things like melting or even devolatilization of the material, which can complicate this type of interpretation substantially. And so the experiments I'll talk about today actually are using pulsed diffraction in order to collect in situ crystal structure information during the shock state. And so in these experiments, we're using high intensity X-rays in order to sort of scatter from our shocked sample. And that allows us to collect the scattered X-rays and construct an atomic level picture of the material that we're interested in looking at. And so really get that in situ information that we're lacking from the sort of more traditional continuum experiments. And so to do this type of in situ diffraction experiments, it really requires using a high flux pulse X-ray source. And so we do these experiments at different facilities. A few of the facilities I'll talk about today include experiments at the Advanced Photon Source, so the synchrotron facility in Chicago. We also do experiments at the X-ray free electron laser source, in particular the LCLS facility at Stanford, which in terms of photon flux and time resolution is really sort of the state-of-the-art tool in terms of getting the most X-rays in the shortest timescale. So this really makes it a good tool to look at complex structural behavior at ultra-fast timescales. And so in the next several minutes, I'll talk about a few experiments using these different facilities. And then time permitting, I'll also talk about some other experiments using a high-powered laser facility called the Omega Laser, which is located at the University of Rochester. And this is a high-power multi-beam laser facility. And this is different from some of these lower-power laser facilities that we have available at light source facilities, in that we can drive samples with complex and tailored pulse shapes using kilojoule pulses. And so this allows us to both get to significantly higher pressures than we can with these smaller laser facilities, but also allows us to explore different types of compression pathways. And so, however, we don't have a X-ray light source facility that's located at these high-power laser facilities, so we have to generate our own light source. And so how we do this is using a technique known as a plasma X-ray source, where effectively we impinge a thin metal foil with a high-intensity laser pulse, and that induces what is helium alpha-like quasi-monochromatic X-rays, which aren't collimated at all. So we collimate them with a metallic pinhole and scatter them from our sample, and then collect data on image plates that we surround our sample with, shown schematically here. So the first experiment I'm going to talk about are actually some experiments from a few years ago now that were conducted while I was a postdoc at Princeton, investigating the shock compression behavior of silica. And so, of course, silica is a hugely important material for Earth and planetary science. And as a result, it's been one of the most highly studied materials under high pressure conditions. And so in particular, the dynamic response of silica is interesting because this is a really abundant crustal material, making understanding the dynamic response important for understanding things like meteorite impacts, where we typically expect natural impacts to generate pressures up to maybe 70 or 80 GPa. And so this makes this experiment really well suited to looking at gas gun experiments, which also have a slightly longer time scale than a typical laser experiment. In addition to these questions about shock metamorphism, shock experiments are also a really important tool for studying the materials of the deep Earth. And as it turns out, we can sort of generate pressure temperature states that are sort of comparable to what you might expect for a planetary adiabat without having to do any sort of additional heating. And so these experiments using shock compression can provide a good tool to look at mineral behavior in the deep earth. And so in particular for SiO2, we can address questions, for example, surrounding understanding silica-rich regions of the deep earth by understanding the structure and equation of state of these materials. And so based on what we know about SiO2, we expect that the 4-coordinated low-pressure structure should transform to the 6-coordinated stishovite phase at relatively modest pressures. However, it's unclear whether this type of transformation will happen on these sort of nanosecond timescales, because it sort of involves a reconstructive phase transformation that may involve diffusion. So this shows the continuum gas gun data that has been in the literature for SiO2. And so from this, we see that we can sort of break the continuum behavior of SiO2 into sort of 3 general regions. It has an elastic limit of around 10 GPa, and then you have sort of this highly compressible region between 10 up to maybe 30 or 40 GPa, which has been described as a mixed phase region. And then above that, we sort of have this incompressible region, where if we compare the slope of this shockwave Hugonio data to the stishovite 300K diamond cell data, they're actually quite similar. And so as a result, it's been widely assumed that the high pressure phase that we form when we shock SiO2 is stishovite. To identify whether this is actually the case, we carried out a series of experiments at a facility known as the dynamic compression sector, which is a beamline at the Advanced Photon Source Synchrotron in Chicago. And this beamline actually houses a 2-stage gas gun in a hutch at the synchrotron. And so the 2-stage gas gun in this photo here is positioned at some angle to the X-ray beam. And so here we see that the target chamber is down here at the end, and the detector is positioned behind the target chamber for experiments in transmission geometry. And so basically how these experiments work is that we have the incoming projectile, and that interrupts an optical trigger that sits a few millimeters in front of the surface of our sample. And that interrupt instigates the collection of a series of diffraction frames during sort of the loading and release process, which lasts around 600 nanoseconds in these experiments. And so using this method, we collected a series of shots up to a peak stress of around 60 GPa, and we collected diffraction data. And from these experiments, we observed that below around 35 GPa, we just observed densification. These are for glass starting material. So here we're starting with an amorphous precursor. And so in this case, we see densification of the glass below around 35 GPa. And then above 35 GPa, we see what is clear crystallization of stishovite. And so it appears that indeed stishovite does form when you shock silica glass starting material. In addition to looking at silica glass starting material, we also looked at alpha quartz starting material, so the stable crystalline phase of SiO2 at ambient conditions. And here what we observed was actually slightly different and pretty interesting, in that at high pressure, we observed what was a clear phase transformation. However, it did not appear to be transitioning to the stishovite structure. And if we compare the diffraction data that we collected for silica glass, shown here in red, to the diffraction data collected for quartz, shown at similar shock pressures, we can see that there's some distinct differences in the diffraction patterns. Notably, we sort of see the absence of this low angle 110 peak, which is really distinctive of the stishovite structure. And then furthermore, if we try to fit this pattern with a stishovite diffraction pattern, we actually get densities that don't really make sense with what we know based on the continuum densities from previous gas gun measurements. And so it appears that we're actually forming what looks like a metastable phase rather than stishovite. starting with alpha quartz starting material. So there's actually a wide range of metastable quartz structures that have been observed in experiments and also predicted theoretically, one of which is a structure known as the defective nickel arsenide type structure. And this is actually a structure that is been observed in laser heated diamond cell experiments, and also in very trace amounts in one report I found from shock recovery experiments using a gas gun. And so this structure actually sort of describes a hexagonal close pack oxygen lattice with random filling of the octahedral sites with silicon. So in a sense, this is actually quite similar to stishovite, because the oxygen, the underlying oxygen sublattice is very similar. However, there's no silicon order within the system. So the silicon is entirely disordered, or in our case, what looks like sort of partially disordered. And so what looks like is happening here is that actually the oxygen lattice responds quite quickly to the loading, and it looks like it sort of rearranges itself into this HCP structure through some sort of martensitic transformation or something that doesn't involve substantial diffusion, whereas getting the silicon ions into the positions that they want to be in what is the thermodynamically stable stishovite structure is more challenging. And so on the sort of fast timescales of these experiments, what we observe is this sort of metastable intermediate that sort of has some degree of silicon order within the structure, however, not full order that we would see for the stishovite phase. And so this is actually kind of interesting because it shows us something about the kinetics of the types of phase transformation that is occurring, and also challenges what's sort of been a long-standing assumption about the structure of SaO2 under shock loading. And then, of course, we can also look at what happens at later times on release. And so here, this is data for polycrystalline natural SiO2 shock to 35 GPa, where we again observe diffraction peaks that are consistent with this metastable structure. And then on release, so at 500 nanoseconds after the shock has transited the entire sample and the sample is brought back to ambient conditions, what we observe is mostly dense glassy material, as well as some amount of what appears to be alpha quartz, which is actually consistent with what's primarily observed at impact sites. And so in conclusion, for our SaO2 experiments, we were able to observe shock crystallization of stishovite for glass starting material, whereas for alpha quartz, we observed a metastable structure, which sort of challenged what we thought we knew about the structure of SiO2 under shock compression. So now I'm going to talk about a second set of experiments where we use laser-driven compression at the X-ray free electron laser to investigate the structure of calcite under shock loading and release. And so we are interested in the behavior of calcite at high pressure and temperature because when carbonate crust gets subducted, it's the stability of carbonate minerals at depth that are important for understanding carbon transfer into the inner Earth. And so understanding things like phase transitions and melting are really important for example, understanding the carbon cycle and potential storage of carbon in the mantle. In addition to these questions about the deep Earth, we're also interested in the behavior of carbonates under shock loading for understanding natural impact events, and this is because they comprise a substantial fraction of Earth's sedimentary rocks. And so as a result, understanding things like potential melting and phase transitions, as well as the potential for processes like impact devolatilization, where calcium carbonate might break down into calcium oxide and CO2 gas are really important for understanding potential natural impact processes. And while these types of processes are difficult to get information about from doing static compression experiments, many experiments have now shown that shock compression can successfully reproduce these effects in the laboratory, or at least many of the natural effects that are observed in different samples. And so in recent years, there's actually been a huge amount of work looking at what is a complex polymorphism in carbonate minerals at high pressure and temperature. And there's actually been a huge number of laser heated single crystal experiments that have now identified a range of complex polymorphs. And so the ambient rhombohedral calcite structure undergoes a series of phase transformations below 50 GPa into different low symmetry phases. This includes things like calcite 2, 3, 6, and 7. And these effectively involve sort of reorientation and tilting of carbonate groups. However, there's still a lot of questions about the metastability and kinetics of these various phase transformations. In addition to these static experiments, there's also was a handful of relatively early gas gun investigations looking at the shock response of both calcite and limestone. And these results identified a phase change by looking at this kink in the continuum Hugonio data at around 20 GPa. However, based on what were the known phases of calcium carbonate at the time, which were calcite 2 and 3, they couldn't reconcile the continuum Hugonio with the thermodynamic behavior of these structures. In addition, there's also been a number of studies that have targeted trying to understand potential impact degassing from gas gun experiments, either looking at the velocimetry profiles that are measured or actually trying to measure gas being emitted during the shock experiment. And these reports are really widely conflicting, where some reports indicate that you primarily see melting, and other reports indicate that you may degas up to 50 mol% at sort of gas gun shock pressures up to 100 GPa. And so this is another question that we'd like to resolve in our experiments. But the real questions we're targeting here are, one, can we identify what the phase change at around 20 GPa on the Hugonio is? Can we also identify at what pressure calcite melts along the Hugonio? And then can we also use diffraction potentially to learn something about possible degassing? And we can do that potentially by observing crystallization of calcium oxide, which would indicate the formation of CO2 gas. And so to address these questions, we did shock experiments at the X-ray free electron laser at what is called the matter in extreme conditions beamline at SLAC. And so here I show a schematic of the experimental setup at this facility. So basically we have these two high-powered lasers, which can reach a maximum pulse energy of around 80 joules. And they're focused onto our sample. And then the X-ray free electron beam comes in, and we collect diffraction in a transmission geometry where we use a series of detectors positioned about the incident beam in order to get good angular coverage in these experiments. So here I delve into some data. This shows a diffraction pattern that was collected for limestone shocked to a pressure of around 25 GPa. And so from this data, we can see that the limestone sample indeed appears to undergo a phase transformation at this pressure. And we can see that if we compare it to various structures that are predicted based on recent structures that have been observed in static experiments, it can be most closely fit by the calcite 6 structure. Actually, calcite 6 and calcite 7 are both compelling candidates, but if you look carefully at the two structures, you can see that calcite 6 actually provides the best fit. And so this is actually a triclinic phase that was recently ID'd by single crystal laser heated experiments by Marco Molini's group. And it's a low symmetry structure. It's a triclinic phase. And so here I show a second experiment at slightly higher pressures. This is at 40 GPa. And again, we see a clear transition to this calcite 6 phase. And here we also have a few ambient calcite peaks, and that's simply because we're using a transmission geometry. And so sometimes when we time our experiment so that the shock hasn't entirely transited the sample. We get some uncompressed material ahead of the shock front in our data. In addition to looking at the structure under shock compression, one unique thing we can also do is we can sort of take advantage of what's really high time resolution that we have at the X-ray free electron laser, and we can sort of collect a time scan. And we do this by collecting a series of experiments using nominally identical samples in the same laser drive conditions. And then we collect diffraction data at different probe times after the shockwave has entered the sample. And so doing this, we can sort of build a series of snapshots as the shockwave goes through the material, and then the material releases back down to ambient conditions. And so here I show one example of this, where we shocked the sample to a pressure around 40 GPa and looked at the structural evolution on release. And so these times listed here are with respect to the shockwave breaking out from the rear of the sample. So time 0 corresponds to the material beginning to release back down to ambient conditions. And so this negative time is for a sample collected on compression. And here we can again index these peaks with calcite 6. However, if we look at the structure evolution in the preceding 20 nanoseconds, we can see that it quickly reverts back to ambient calcite without any indication for calcium oxide formation, which might indicate degassing. And so it appears that we don't see any evidence for degassing, at least from this pressure. And then finally, here I show a diffraction pattern where we observed melting of calcite at around 60 GPa. And so in this case, at the highest pressure, we no longer see crystalline diffraction peaks. And so we understand that as our sample having melted. Again, we have this strong diffraction peak from uncompressed material, but the bulk of the sample appears to be consistent with liquid material. Here I show a slightly higher pressure molten experiment. And also alongside it show in this blue trace the same drive condition. So here we're shocking the sample to around 80 GPa, and then this is collected at 20 nanoseconds out. So in which case we can understand the sample as being fully released. And again, we see what appears to be ambient calcite structure. And so gas gun experiments have observed or been interpreted as understanding potential degassing at pressures below 50 GPa. If you look at some of the models that have been carried out, it suggests that you might need to get to slightly higher pressures to see any significant degassing. However, at 80 GPa, we might expect, based on these models, that we would see some indication of this. However, from our experiments, we really don't see any indication of calcium oxide formation, which would suggest that we had substantial degassing occurring. And so this is just sort of a summary of these results, where I show the densities that were determined from fits to the diffraction pattern. And we can see that these are in overall good agreement with the pre-existing continuum Hugonio data. And so our results are broadly consistent with the expected properties of calcium carbonate along the Hugonio. And so in summary for these calcite results, we saw what was a crystallographic phase transformation to this calcite 6 phase and melting along the Hugonio at 60 GPa with a reversion to the calcium carbonate ambient structure on release for all pressures that we looked at without significant evidence for any sort of degassing occurring. And then furthermore, I'll just point out that when we're looking at what are these sort of types of low symmetry structures using an experiment at a facility like an X-ray free electron laser, where we have really unprecedented X-ray flux, allows us to sort of differentiate between these different low symmetry structures in a way that we really wouldn't be able to at any other facility. So now I'm going to change gears again a little bit and move deeper to the core. And in these experiments, we're really interested in understanding the structure and properties of core materials at conditions both of Earth's core as well as the cores of larger super-Earth exoplanets. And so we know, of course, that Earth has a liquid outer core and a crystalline inner core with pressures ranging between 136 GPa at the core mantle boundary to around 360 GPa at Earth's center. And we also know that the core is iron alloyed with nickel and around 10% lighter elements, where, of course, candidates are things like silicon and carbon. But furthermore, outside our solar system, we also now know that there's a big population of what are effectively scaled up Earth-like planets, or super Earths, which have masses up to 10 Earth mass, and substantially potential higher pressures in their interiors as a result. And so we expect also that the cores of rocky exoplanets potentially also incorporate light elements as well, including carbon, which motivates sort of extending these studies also to higher pressures beyond the 360 GPa that we might expect for Earth. So why do we care about light elements in the core? One good reason is that it's expected that alloying with light elements will substantially affect the melting behavior. And so because we have a liquid outer core that coexists with a solid inner core, understanding the high pressure melting behavior of these types of alloys is really important to put constraints on core temperatures. But also the presence of this liquid outer core really allows for potential dynamo formation. And so that is believed to play an important role in planetary habitability. And that's really determined by the relative slope of the liquidus and the planetary adiabat. And so when we start to think about other planets like super Earths, understanding the melting behavior at significantly higher pressures then becomes important for predicting whether these planets may have a dynamo. In addition to understanding the melting behavior, we're also interested in understanding the solid state behavior at high pressure. And this is because we're interested in understanding crystallization of Earth's inner core. And actually, we know that the structures of Earth's inner core are really heterogeneous. And the source of some of these heterogeneities is believed to be related to crystallization of light element rich alloy phases, where sort of changes in crystallization over time could affect sort of the concentration of light elements in the precipitating solid that may give rise to some of these signatures that are observed from geophysics. So our experiments are targeted at understanding carbon incorporation into the core. And in particular, for the iron-carbon phase diagram, there's actually quite poor understanding of this phase diagram at pressures above a few hundred GPa. What we do know is that carbon has pretty limited solubility in HCP iron, and so these cores likely contain carbide phases. However, if we look at different models, which are based on long extrapolations of low pressure data, there's some disagreement as to what would the first phase to crystallize from the melt would be, whether that would be Fe3C or cementite or Fe7C3, in which case Fe3C would then melt incongruently at high pressures, breaking down into an iron-carbon liquid alloy and Fe7C3. However, there's really no experimental data at the direct conditions of the inner core or the cores of the larger super Earth planets. And so that's one of the things our experiments are targeted at. And so we're interested in understanding what the structure of Fe3C is under shock compression. And we're also interested in understanding whether we can put any constraints on the iron-carbon melt curve at pressures above 100 GPa. We're actually looking at melting through shock experiments can be pretty useful because we can directly observe that by looking at the loss of diffraction peaks along the Hugonio, but then we also have an independent measure of density from our velocimetry measurements. And so in these experiments, we're really interested in investigating carbide phases in Earth's inner core, and also understanding how carbon might suppress the liquidus at Earth core conditions. And so for these experiments, we actually used high pressure synthesis. And so these samples were synthesized by Yue Fei and Hu, and they were able to synthesize what was around 98% dense sintered polycrystalline samples using a cubic multi-anvil press. And this is really critical, in particular for shockwave experiments, that we can sinter really dense samples, because if we have a high degree of porosity in our sample, that can give rise to a heating during the experiment, because effectively when you shock a sample, that pressure volume collapse is oftentimes translating to heat. Sorry, my dog is barking if you hear that in the background. So by using a really dense sample, we can be certain that we're actually staying on the thermodynamic Hugonio curve rather than some sort of hotter curve that's hard to predict. And so these experiments were carried out at the synchrotron, also at the dynamic compression sector, but in their laser compression hutch. And so this in many ways is similar to the experiment at the X-ray free electron laser. However, we have slightly less photon flux in these experiments. And so similarly, we shock the sample with a high-powered pulse laser with energies up to 80 joules and typical pulse widths of 5 or 10 nanoseconds. And then we probe the sample in the uniform compression shock state with the synchrotron X-ray beam. And so here I show some data from these experiments. I show an experiment that was collected at 156 GPa. And here we see that at this pressure, we can index all the peaks using the Fe3C crystal structure. And so it appears that up to this pressure, we haven't undergone a phase transformation. And then if we go to slightly higher pressures, up to 173 GPa, we observe a diffraction pattern which is consistent with a liquid, which is actually interesting because we observe what appears to be sort of direct melting to a single liquid along the Hugonio versus any indication that we have coexistence of liquid and solid, or potential breakdown to Fe7C3 and an iron liquid alloy, which is what we predicted what would happen based on sort of both static experiments as well as our understanding based on theory. And so this may be a kinetic effect, and it's actually interesting as well that the liquidus is fairly low in this case compared to what we would expect for iron, where iron actually melts at around 260 GPa along the Hugonio. So this is nearly 100 GPa below, and several, and so the temperature difference is significant. And so from these experiments, we were able to sort of learn about the shock compression behavior, so up to pressures of around 250 GPa. However, if we want to understand higher pressures, we do, instead of shock compression experiments, we do what are known as ramp compression experiments. And in these experiments, instead of compressing a material along the Hugonio, we try to compress a material along a quasi-isentropic pathway. And so this is shown schematically as this green curve. And one of the main goals of this is that when we shock a material, most materials melt at a pressure of around 200 to 300 GPa, or most iron alloys would melt in that range. And so we want to study the solid state behavior at higher pressures. It requires that we move away from doing shockwave experiments and look instead at using different types of laser pulse shapes in order to explore off Hugonio pathways. And so in the next set of experiments I'll talk about, we did what are known as ramp compression experiments of Fe3C up to a peak pressure of 600 GPa. And here we're really interested in understanding what the structure of iron carbide is at higher pressures, potentially moving to super Earth cores, and in particular looking at whether we observe decomposition into ACP iron and higher carbon content carbides, for example, Fe7C3 or Fe5C3, which are predicted theoretically. And so for these experiments, as I mentioned, we use, rather than shock compression, we use what's known as ramp compression. And to do this, we tailor the pulse shape that we use with the laser to have a more gradually increasing pulse shape. And so this allows us to explore the range between the Hugonio and the isentrope. And so this sort of allows us to get to conditions that are expected for larger planetary interiors. And so this is sort of shown schematically here, where we can pursue this sort of ramp compression pathway shown in blue, as opposed to melting at around 200 to 300 GPa. And this is particularly important when we're starting to think about, for example, super Earth planets. And so, as I mentioned, these experiments are carried out at a high-powered laser facility, in particular the Omega laser facility at the University of Rochester. And so here we use this type of ramped pulse shape, which allows us to put ourselves along, ideally, the isentrope. And then again, we use diffraction experiments by impinging a metal foil with a high-intensity laser pulse, scattering from our sample at maximum compression, and then collecting diffraction data on these image plates that surround our sample. And so here I show an experiment where we ramped our Fe3C sample up to a peak stress of around 370 GPa, so near central Earth pressures. And again, we also observed what is the Fe3C orthorhombic structure. So we did not observe a phase transformation up to this pressure, nor did we observe any evidence for breakdown into other carbide phases or ACP iron. And so it appears that we're either metastably maintaining this material up to these pressures, or potentially iron carbide is more stable than had been previously thought. And so in conclusion for our discussion of iron carbide, we were able to observe melting along the Hugonio at around 160 GPa into a single liquid, so no evidence for incongruent melting. And then we observed the structure up to 600 GPa, but we did not see any evidence for a phase change. And these experiments really raised questions, in particular about understanding the kinetics of these types of dynamic compression experiments. And in future experiments, we're actually targeting different means of trying to overcome these kinetic barriers in order to sort of better understand the application of these results to planetary interiors. And so in the next just minute or two, I wanted to briefly mention how a facility or the sort of capabilities that a facility like Forest can be really valuable to the types of experiments that we're doing in these types of dynamic compression field. And so, as I mentioned, the ability to alter the starting density of the material has a really strong effect on the pressure temperature path that you follow in a shock compression experiment. And so this can go one of two ways. Either when you're using a porous sample, you get a lot of extra heating that occurs. That puts you on a much hotter compression pathway. And alternatively, if you're using a dense polymorph, then you follow a much cooler compression pathway. And so by having the ability to synthesize materials of variable densities, that then allows you to explore different regions of pressure temperature space. And so it allows you really to explore the phase diagram of materials in sort of a unique way. In addition to that, when we have materials that undergo several low pressure phase transitions, that can make doing different types of loss symmetry and equation of state methods really challenging. And so if we can start with a high pressure polymorph, that can really reduce the errors in our equation of state measurements up to the highest pressures. And then, as I mentioned, a lot of materials also melt at around a megabar along their shock hugonios. And so if we want to look at their material behavior at higher pressures, in addition to doing sort of the tailored pulse shaping experiments at what are really expensive to run and operate laser facilities, we can also attempt to synthesize denser starting materials, and that then allows us to follow a cooler compression pathway as well, getting to sort of higher pressures without melting a material. And then one additional thing is that, as was probably evident from some of the projects that I discussed today, a lot of these experiments are really hindered by kinetics, and understanding the kinetic barriers that may limit solid-solid phase transitions or result in the need to significantly overdrive a phase transition are problematic for a lot of these types of ultra-fast experiments. And so we're lucky, though, in that doing high pressure synthesis can really address a lot of these questions, I think. By synthesizing high pressure polymorphs, we have the ability, as I mentioned, to really explore a wide range of phase space. But also, in many cases, synthesizing high pressure polymorphs can really even look at synthesizing metastable structures that may transform more readily to a high pressure phase. And so in many cases, if you start with a metastable structure, for example, starting with silica glass as opposed to crystalline silica, that sort of promotes crystallization of the stable crystal structure under shock loading, or also could potentially promote crystallization of novel high pressure metastable structures as well. And so this is a really interesting area for exploration. And so I'll mention briefly two sort of sets of experiments that are using these types of ideas. The first is postdoc Dong-Hoon Kim, who's a Carnegie Fellow working with myself and Yume Fei, has been doing a lot of work recently looking at synthesizing different high pressure silicate polymorphs, and then doing experiments both at the X-ray free electron laser, as well as using pulse power experiments to get to very high pressures using this facility, which is the Z machine at Sandia National Lab. And so in these experiments, he's interested in looking at dense starting material in order to understand silicate melting at high pressures. And then in the second set of experiments, we're interested in looking at different carbon materials. And in particular, we're interested in using the multi-anvil press to synthesize what is dense amorphous carbon. And so it's actually understood that using the multi-anvil press, you can actually tailor the sp2 to sp3 content in an amorphous material. And so by doing this, we can actually explore a wide range of pressure temperature space, and also potentially overcome some of the kinetic barriers that prevent formation of what is expected to be stable phases for carbon at ultra high pressure conditions. And so this is something that we're planning experiments on right now, and looking at getting started with the synthesis. And in particular, if you can get use for example fullerene precursors, and this was done in this recent Nature paper, you can actually synthesize nearly 100 sp3 content amorphous carbon that's pretty transparent, in which case we could do both equation of state and temperature measurements along the shock hugonio using this decaying shock technique, which sort of collects a series of data in one experiment, which gives us information about the latent heat of melting and identifies melting along the hugonio curve. And so these are experiments I'm doing in collaboration with Yvonne Olnick from the University of South Florida. And so this is just a few ideas about different ways that you might take the ability to have capabilities for high pressure synthesis and apply them to these types of measurements to do what I think are interesting things. And so I of course wanted to acknowledge my many collaborators in these experiments from a wide range of institutions as well as national laboratories. I'll leave this up and hopefully invite any questions that people may have. So yeah.
Thank you, Sally. Okay, we have a couple questions in the chat. We have a couple minutes left here. First, Crystal Fudge asks, did coesite form or survive in your experiments on the SiO2 system?
No, we did not see any evidence for coesite.
Okay. And then Bin Chen says, nice talk. Is there any difference in structural evolution by shock loading if your starting material is SiO2 glass or crystalline SiO2, i.e. quartz?
Well, so is there any difference in structural evolution? So it's actually interesting in that sort of range between 10 to around 40 GPa that's sort of highly compressible. In alpha quartz study material, that's actually what I would describe as sort of a true mixed phase region, in that you see a combination of the metastable high pressure phase and compressed alpha quartz starting material. Whereas for silica glass, you only see densified silica glass. So that's sort of a difference in the evolution of the behavior at different points along the shock hugonio. However, it's important to understand that when you shock a material, you're not actually compressing the material along the hugonio. The hugonio is like a sort of a series of endpoints. You actually compress it along a straight line because it's sort of a instantaneous jump from ambient to the high pressure condition. So that's not reflective of the pathway the material goes through during the experiments. But also when you do SiO2 glass, you're slightly hotter because the material is slightly less dense than alpha quartz. And so for that sort of volume collapse heating reason, you do have slightly more heat available.
Okay. Do we have any more? Vincenzo says thank you. Do we have any more questions from the audience?
I do have one. So in Shim's group, like I was working with Shim's group on SiO2 also, but we also had H2O in our experiments, and we also saw that nickel arsenide structure quite strongly, but it was actually stable as far as we can tell. In that case, it was with H2O. So it was probably entropy stabilized because of hydrogen and silicon substitution. So yours is sort of time stabilized, right? It's like stable, not really stable, but metastable for a short time. And so was the dry experiments in the diamond cell by Vitaly Prokopenko.
Yes. Yeah.
So I guess all I'm saying is it could either be entropy stabilized like ours was, and it was very stable under laser heating for a long time, as long as we could basically heat. But it's really interesting that it can be stabilized two different ways. I guess that's what I want to say.
Yeah, no, I was very keen to read that paper when it came out, because it was when we were thinking about these experiments. And so, we're generating a lot of entropy when we shock a sample. So it's likely that's the source of the disorder.
Yeah, that's right. Yeah, you're right. You're right. Because also entropy could stabilize a disordered phase at high temperature for a little while until it's quenched. So yeah, it's pretty interesting.
Okay, we have one last question before we go. From Dan Shim. He says, I'm curious about how a composite material would respond to shock. I wonder, for example, how small grain of a phase in a matrix of other material would respond to shock. I wonder if that can give a way to get better diffraction measurements with less stress gradient.
So it's my understanding that when you have heterogeneities in your sample, you're going to get you get a lot of reverberations potentially. And you also potentially can form sort of hot spots where energy doesn't partition uniformly into the sample. So it's a really interesting question. And actually, when we're thinking about like geologic materials, it's a really important question. And a question that I think there's a lot more work needs to be done to better understand that. So I don't fully have an answer to that question, but it creates a lot of potential complexity both for experiments as well as for modeling. But it is important for understanding mixtures, in particular in sort of geological and planetary science, for sure.
Okay, there were a couple more comments in the chat, but I've copied those down. I'll send those to you afterwards. And thank you for everyone for attending. And thank you to Sally Jean Tracy, our first speaker.
Thank you. It was
We'll
fun.
see you all in a month for Bin Chen.